Ohm's law. OHM, Ohm's law. Ohm's law in electric current. Na? So what it says, Ohm's law states that at first means at constant temperature, because temperature, varying temperature may change our result. Okay, at constant temperature the current flowing through a conductor of uniform cross sectional area, conductor which of uniform cross sectional area, no, is directly proportional to the difference of potential applied, or just you can write across the two ends of the conductor. ACROSS, across the two ends of the conductor. Okay. That means if we have some conductor, suppose first thing, at a constant temperature, we are not going to change the temperature. The current flowing a conductor of uniform cross-sectional area. So let's draw a conductor of uniform cross-sectional area. It has same cross-section throughout the length. Okay. If a potential difference across the conductor is V, potential difference is V, and current through it is I, then according to Ohm's law, V current is proportional to potential. Okay. That's the thing. Okay, this is the simple. Okay. So before we have studied the relation between current with the drift speed. No, there is a current, means if I have some potential, that is V plus and V minus. So which way current will flow? Low potential. This way electron will flow, but current will flow in this direction. No? Electron will flow in the opposite direction, to the lower potential to the higher potential. Okay. Okay, and by convention we choose current direction is the opposite to the direction of flow of electrons. Okay. Before we know, I current is proportional to drift speed, that is it's related like NEA BD. Okay, where what is N? Number of, what is that? It's free electron density. Density inside the material, inside the conductor, means number of electrons per unit volume. E is the charge of electron. A is the cross sectional area of the electron of the conductor. Cross sectional area, which we choose uniform, otherwise we cannot define the relation like this. Okay, and Vd we know drift speed, or what we call drift velocity, drift speed of electron. Okay. Then we will use two relations. First relation is, we know if potential difference is V, that is V plus minus V minus, potential difference, and length is L, then what is the electric field? Electric field inside the conductor. Since we are applying potential difference, there is possibility that there should be a electric field inside a conductor. If we will not apply any potential difference, then electric field inside a conductor is zero. Okay, we know earlier now, if conductor is placed inside any electric field, then net electric field is zero inside that. Or if we give some charge to a conductor, so charge will come to its surface only, it will make electric field is zero inside the conductor. That is different. But here we are applying potential difference. Electron has to move. Electrons will always experience an electric field. That means electric field is always present inside the conductor as long as potential difference is maintained. Okay. So electric field inside the conductor, it's a uniform shape. We can write E is equal to potential difference divided by length. If it is length is L. Okay. Total length is L. Okay. L is length of the conductor. Okay. And one more thing, we have the relation of VD with electric field. VD with electric field. Can you remember? E by 2A, then tau. Okay. So tau is relaxation time, na? Time of electrons, no, of free electrons inside that material. Okay. So in place of E, now substitute this value V by L. So VD becomes E tau by 2m V by L. Now substitute this VD here. This is suppose equation 1. So substitute in equation 1. What we get? Current is equal to N E. Okay, first write, then we will next rearrange them. Okay, N E A V D. In place of V D, we will write V by E M 2 M L into V, potential difference. So this is N E E. There is 2 E square A tau by 2 ml V. Okay, so this is the complete relation between current and potential. Okay, this is a constant quantity, right? Here N for the material, if we are not changing the material, if we are taking at constant temperature, we know with the temperature the tau varies, the relaxation time changes, na? More the temperature, relaxation time decreases. Temperature increases means relaxation time decreases, inversely proportional. No. And if you are not changing this conductor, means we are not changing its shape and size. That means its cross section will be fixed. Its length will be a constant quantity, is not going to change. So mostly this part is a constant. We represent this part by 1 by R, where R is equal to inverse of this 2 ml by n e square a tau. R is called resistance. Okay, resistance of the material. No. And what is 1 by R is called? Inverse of resistance, nahi? Conductance. Inverse of resistance, that is conductance. Okay. So from here we can write, that implies V is equal to IR. This is the mostly we will use this relation. VIR, 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 Vir. Easy to remember. Vir, VIR, VIR. Similarly, current I is equal to NAVD, NAVD. Just repeat for few times. Okay, you can easily remember NAVD. Okay, so this is V is equal to IR, and what is R? That is 2 ml by N E square A tau. Okay, if some copper material is given to you, the conductor is made up of copper. Okay, some amount of copper is given, so you are supposed to make some some wire using that copper. Okay, that means it depends on you how thickness will be, how long will it be. No, it depends on you. Okay, that means these two quantities depends on the geometrical shape. L and A, L and A depends on geometrical shape. Huh? Mass. This is mass of what? Electron. So it doesn't matter which material you are taking or what is its set, no. And the rest thing, if I just remove this thing, rest thing I will write like rho is equal to 2m by n e square tau, no. This thing is the property of the material. It's not doesn't depend upon its geometrical shape and size. It is just the property of the material, no. No, this resistivity, it varies from material to material. N e square, n sorry, m and e square are the constants. Just forget, like 2, we cannot change 2, we cannot change the mass of electrons, we can change the charge of the electron. Those are constant, so no need to talk about them. What are the two things? That is number density, free electron density, and relaxation time. These two are specific to a material. Okay, if we change the material, copper to sodium, sodium to iron, iron to gold, these two things will get changed. Okay, so these are material property. This term is known as, this rho is known as specific resistance, is called as specific resistance or resistivity, 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 resistance of the material. No, I have written here, girl, something wrong. Resistance of the conductor, not material, of the conductor. Okay, it is resistivity of the material, material of the conductor. Is it clear? Okay, that is of the conductor. Material, if I choose write only material, that means it is doesn't depend upon shape and size. It's material. Copper means copper. Doesn't matter which shape it is. It is circular, it's spherical, cylindrical. That is always copper. Okay, but this R depends on the resistance. We cannot write. It's a property of it's a resistance of the material. It's the resistance of the conductor as a whole. This thing is resistivity of the material of the copper. Whether it is copper, material to material. Yes, relaxation time. So it changes from material to material. It also changes with the temperature. No, it also changes with the temperature. Since tau changes with the temperature. No? So tau. So now let's write the relation between. It's proportional to more the temperature, more is the resistivity. Yeah, this resistivity. So use these two equations to write the relation between R and rho. We can write R is equal to rho L by A. Okay. Oh. Like 1 by rho is known as conductance. Similarly, 1 by rho is known as resistivity. Its inverse is conductivity. Conductivity. It is not. Its symbol is sigma. Okay, we use the symbol sigma. Okay, is it okay? There is another form of Ohm's law. There is another form of Ohm's law. Okay, here we compare two quantities are potential and current. Both are scalar quantities. There is another form, that is vector form of Ohm's law. What is that? What is that? We will use this equation. Okay, we will use this equation. This, suppose this is equation is right, 2 number equation. This is 3 equation. So from equation 2, we can write, you divide by a both sides. So I by a, what will be the right hand side? N e square tau by 2m v by L. What is I by a? What is I by a? Current per unit area. Current density. That is current density. What is N e square by tau by 2m? N e square tau by 2m. What is 1 by rho? This is rho. RH or rho. So 1 by rho, conductivity, sigma, and V by L, electric field. So here current density is also a vector quantity, E is also a vector quantity. We can write like this. This is another form of Ohm's law. Okay, another form of Ohm's law. Okay, just one point. Okay. So I have derived this relation for a conductor. It doesn't mean that every conductor obeys this rule, obeys this law. Every conductor do not obey this law, Ohm's law. Those obeys conductor, those obeys Ohm's law. Conductors, those obeys Ohm's law are known as ohmic conductors. Okay, unless they are known as non-ohmic conductors. Okay, so this is just a direct relation, no? V and resistance. If you draw graph between V and I, it will be a straight line, no? Passing through its origin. No, we'll see that later. Okay.